In the name of Almighty God, I am Mahsa Hassan Kosher, and today I want to talk about fatigue analysis of a wheel rim. High cycle fatigue, or HCF, is a failure in materials that happens after a large number of stress cycles, typically more than 10,000. It is caused by alternating stresses between the material's elastic range, meaning the deformation is minimal, and elastic, not plastic. Examples include rotating parts like shafts and gears, aircraft wings, and springs. And what are the characteristics? The first one is cycles. Cycles happens over a very high number of cycles, sometimes millions before failure. The next one is stress strain. Involves relatively low stress and stress amplitude which are primarily elastic. The next one is failure. The failure often appears brittle and sudden with little to no visible plastic deformation occurring beforehand. The next one is caused by alternating stresses that are below the material's yield strength. And what are the examples? The first one is rotating parts, shafts, gear, and turbine blades in engines and machinery. The next one is the structural components, bridges, aircraft wings, and offshore structures subjected to repeated loading. The next one is automotive parts, springs, and connecting rods in cars. And what are the related concepts? The first one is a low cycle fatigue or LCF. This is the opposite of HCF. It happens in a low number of cycles, typically fewer than 10,000, and involves significant plastic deformation because the stress is higher than the yield strength. The next one is SN curve or Wöhler curve. This curve is used to characterize a material's fatigue performance, showing the relationship between stress S and the number of cycles to failure, which is mean N. FCF is the region of this circle at high N values. The next one is very high cycle fatigue or VHC. F. A newer area of study concerning fatigue failures that happen after even more cycles, sometimes 10 to 9 cycles or higher. High cycle fatigue or HCF is defined as a type of fatigue that happens from a small elastic strains under a high number of load cycles before failure, characterized by combined mean and alternating stresses, primarily involving elastic deformation and typically resulting in failure without significant macroscopic plastic deformation. The next one is typical service-induced damage, high cycle fatigue or HCF. High cycle fatigue or HCF is characterized by its low stress amplitude and high frequency. In this case, stress is typically below the material's yield stage and produces a small elastic strain. The latter, compounded over a large number of cycles, lead to failure, typically over 1,000 to 10,000 cycles. The specific number of cycles corresponding to a high cycle fatigue versus a low cycle fatigue fracture depends on the actual material behaviors. High cycle fatigue is particularly concerning for gas turbine blades and a critical factor in their design. This is because turbine blades are exposed to complex vibratory inputs from self-excited sources, such as flutter to aerodynamically imposed vibrations. An example of the latter includes the nozzles passing harmonics, downstream blades, combustion-originated oscillations, and a wide range of service-induced causes such as wear. Nozzles are very important sources of vibrations due to their proximity to the blades and their complex harmonic content. Frequency waves generated by the high velocity gases crossing the upstream nozzles, for instance, cause repeated bending in the passing blades. Changes due to variation in the nozzle throat areas or rotor speed affect the frequency of the blade's associated loads. This can manifest itself in undesired frequencies that coincide with the blade's natural frequencies, creating conditions of resonance. Under the normal circumstances of operation and associated service activities limited to no change in the blade's natural frequencies is foreseen. Unlike their larger steam turbine counterparts, there remain some exceptions to the prior statement, including certain designs, especially for the latter turbine states. As the dominant strain in HCF is elastic, respective fatigue life is characterized using stress rather than strain on a stress life (SN) plot. The cycle stress is plotted versus the logarithmic scale of the number of cycles to failure. And what about the design and applications? Design applications for high cycle fatigue, as illustrated here and can see in simulation, is a critical desired condition for gas turbine engines. Components are subjected to vibratory excitation induced by airflow on airfoils or the white noise acoustic environment of nozzle component. Metals are typically assumed to have a fatigue run out condition. For example, there is no further strange degradation after a given number of cycles, generally 107 or 108 cycles. CMSs cannot be assumed to have a run-out condition since environmental degradation is a function of time. Therefore, ideally, full-life testing is desired. But lacking this data, the end-of-life strength is estimated based on degradation rates obtained from accelerated life tests. Eventually, full-life testing is required to validate these assumptions. The life of a C component is influenced by the number of cycles encountered as well as the time at maximum load. Also, for CMSs, the time at temperature is generally more detrimental to the life than the number of cycles. Also, the life is affected by the synergism between the time, temperature, environment, and stress as defined above the for LCF tests. The effects of material damage on HCF performance should be evaluated in a manner similar to that defined above for LCF material performance of damaged material. The next one is durability and reliability in diesel engine system design HCF. High cycle fatigue is a type of fatigue caused by small elastic strains under a high number of load cycles before failure happens. The stress comes from a combination of mean and alternating stresses. The mean stress is caused by the residual stress, the assembly load, or the strongly non-uniform temperature distribution. The alternating stress is a mechanical or thermal stress at any frequency. A typical loading parameters in engine HCF is the cyclic cylinder pressure load or component inertial load. HCF requires a high number of loading cycles to reach fatigue failure, mainly due to elastic deformation. It has lower stresses than LCF, and the stresses are also lower than the yield strength of the material. HCF usually doesn't have microscopic plastic deformation as large as that in LCF. The dominant strain in HCF is mainly elastic. In contrast, the dominant strain in LCF is plastic. Typically, HCF examples are the cracks at tangential intake ports connected to the flame deck on the water side of the cylinder head, the valve seat area, the piston, and the crankshaft, and the connecting rod. Because HCF is governed by elastic deformation, stress is usually a more convenient parameter than strain to be used as the failure criterion. The HCF life of the component is usually characterized by a stress life curve, for example the SNF curve, where the magnitude of the cycle stress is plotted versus the logarithmic scale of the number of cycles to failure. The design basis loads and qualification, what would be a good overall engineering evaluation approach to fatigue. In a broad sense, we could divide the question of fatigue damage in two general categories: high cycle fatigue and low cycle fatigue. In the case of high cycle fatigue, the stress amplitude is small but the number of cycles is so large that the designer must either keep the resulting stresses below the material endurance limit or eliminate the cause of high cycles. High cycle fatigue is typically of FIV or thermal cycling. Low cycle fatigue consists of events causing large swings of stress. Low cycle fatigue is typically caused by plant transients, large pressure or temperature fluctuations from unique events such as rapid heat-up or cool-down, or safety injection of cold water into a hot system. Unlike high cycle fatigue, low cycle fatigue events can be defined individually and can therefore be analyzed and accounted for in the design life of the component. Very high cycle fatigue at elevated temperatures. A review on high temperature ultrasonic fatigue. Currently, high reliability and extended fatigue life are among critical needs for the engineering of fatigue-critical components. The term very high cycle fatigue or VHCF is used to define a domain of fatigue in which materials fail under extended cyclic lives beyond 107 cycles. In several industries such as aeronautics, high-pressure compressor blades, hypersonic technology vehicles or HTF, and unmanned aerial vehicles or UAV, high-speed trains, and ground transportation, many components are exposed to repeated loads of low amplitude and high frequency, several times more than 10 million cycles during services. In almost all these applications, the components are exposed to high-frequency cyclic loadings and severe environments during operation, say jet engine parts. To this end, exotic materials needed to be developed to withstand the harsh environment associated with hypersonic flights and very high loading frequency. For instance, due to the acoustic loading caused by aerodynamic flow and engine noise. The critical fuselage panels of hypersonic cruise vehicles will be subjected to combined extreme environment. For example, acoustic loading of more than 150 decibel overall sound pressure levels, up to 10 kHz, and estimating the consumed remaining lives of components under these combined extreme environments requires approaches that account for the mechanism associated with crack initiation rather than the phenomenological approach alone. Other examples are turbine blades of the airplane's engine, where the fatigue life is around 1010 cycles at elevated temperature. In turbine blades, fatigue is mainly caused by force and non-synchronous vibration at elevated temperature, where the mean stress may not necessarily be zero or fully reserved. For various aerodynamic and mechanical reasons, the stress amplitude is relatively low but the cyclic frequency is high. This leads to many cycles accumulated over a short amount of time, which presents a major risk to aviation equipment safety. Fatigue testing. High cycle fatigue. In most structural components designed for long operational life, the working cycle's stress levels are generally below the yield strength of the materials. The high cycle fatigue data is generated either in rotating beam machines or in an axial push-pull machine under fully reversed cyclic loading, which R is equal to minus 1, are graphically presented as stress line or SN curves, as shown here. It can be seen here that compared to a smooth species, a specimen would with a notch would fail at a much lower number of cycles for a given stress amplitude. In the nearly horizontal portions of these curves, some data points shown with arrows to the right are indicative or run outs, which implies test discontinuation at the corresponding number of cycles. The asymptote to these nearly horizontal portions of the two curves indicates the fatigue limit or the endurance limit. A steam turbine retrofitting for the life extension of power plants. Fatigue. When a metal is subjected to repetitive stress, a crack happens on the surface and propagates, resulting in an eventual failure at a lower stress than that required for failure on a single application of load. This phenomenon of failure, which happens under cyclic loading, is termed a fatigue failure, which is characterized into two types: high cycle fatigue and low cycle fatigue. Delamination propagation under cyclic loading. For high cycle fatigue, according to Lemaitre and colleagues in 1999, high cycle fatigue happens when the damage is localized at the microscale as a few micro cracks. The number of cycles to failure is greater than 104 for high cycle fatigue. A cycle by cycle analysis is computationally impractical. Therefore, a two scale computation is usually adopted. Damage evaluation is extrapolated over a given number of cycles using this strategy called cycle jump strategy. The computation of the whole load history is reduced to a selected number of cycles. High cycle fatigue models require the definition of the relation between the damage variable and the number of cycles as an input for the cycle jump strategy. The cycle jump strategy controls the accuracy of the solution by means of the number of cycles to be skipped in the analysis. There are different approaches in the literature to control the accuracy of the solution. Van Pigman and his colleague computed the cycle jump length by limiting the maximum increment of the damage variable at each cycle jump. He developed a similar cycle jump strategy where the cycle jump starts after checking in a cycle by cycle calculation that the damage variable evolves. Monotonically, uh, and other researchers presented a similar model with an improved control of cycle jump length. A majority of the model relating the damage variable or mechanical properties to the number of cycles use a phenomenologically law established prior and formulated as a function of the number of cycles. The damage evaluation law is a function of several parameters that have to be adjusted to calibrate the number model with experimental results, usually by trial and error. The lamination propagation under cycling loading, high cycle fatigue. According to a researcher in 1999, high cycle fatigue happens when the damage is localized at the macro scale as a few macro cracks. The number of cycles to failure is greater than 104 for high cycle fatigue. A cycle by cycle analysis is computationally impractical. Therefore, a two scale computation is usually adopted. Damage evolution is extrapolated over a given number of cycles. Using this strategy called cycle jump strategy, the computation of the whole load history is reduced to a selected number of cycles. High cycle fatigue models require the definition of the relation between the damage variable and the number of cycles as an input for the cycle jump strategy. The cycle jump strategy controls the accuracy of the solution by means of the number of cycles to be skipped in the analysis. There are different approaches in the literature to control the accuracy of the solution. A researcher computed the cycle jump length by limiting the maximum increment of the damage variable at each cycle jump. They developed a similar cycle jump strategy where the cycle jump starts after checking in cycle by cycle calculation that the damage variable evolves monotonically. A researcher presented a similar model with an improved control of the cycle jump length. The majority of the models relating the damage variable or mechanical properties to the number of cycles use a phenomenological law established prior and formulated as a function of the number of cycles. The damage evolution law is a function of several parameters that have to be adjusted to calibrate the numerical model with experimental results, usually by trial and error. And what about design and applications? High cycle fatigue test. HCF, as illustrated here, is a critical design condition for gas turbine engines. Components are subjected to vibratory excitation induced by airflow on airfoils or the white noise acoustic environment of nozzle components. Metals are typically assumed to have a fatigue run-out condition. For example, there is no further strange degradation after a given number of cycles, generally 107 or 108 cycles. CMS cannot be assumed to have a run-out condition since environmental degradation is time-dependent. Therefore, ideally, full-life testing is desired, but lacking these data, the end-of-life properties are estimated based on degradation rates obtained from the accelerated life test. Eventually, full-life testing is required to validate these assumptions. The life of the CMS component is influenced by the number of cycles encountered as well at the time at maximum load. The same general procedure is followed for HCF testing as was described for LCF testing. Expect that dwell time at maximum stress is kept at minimum and cycle test frequency is increased for HCF and the total number of cycles is increased significantly. The requirements for moisture conditioning, pre-cracking, and stress overload are essentially the same for HCF and LCF testing. Since time at maximum stress and temperature are key contributors to accelerated degradation rates, HCF testing has a low priority in the killer test matrix than the stress rupture or LCF tests. Delamination propagation under cyclic loading, low cycle fatigue. According to a researcher in 1999, low cycle fatigue happens when the damage is localized in domains of stress concentrations, but it can be measured and evaluated at the mesoscale. The number of cycles to failure is smaller than 104. Low cycle fatigue models account for fatigue damage evolution on a cycle-by-cycle analysis, defining in the majority of the model an evolution of the damage variables during the unloading pass. Within the context of the cohesive zone model, there are several models that extend cohesive laws that were derived from monotonic loading into forms suitable for cyclic loading. Researchers developed a cohesive law that describes separately the unloading and reloading processes and creates a hysteresis loop between unloading and reloading passes. Researchers describe fatigue crack growth by incorporating a damage evolution equation for cyclic loading. And other researchers developed a cohesive zoom model for cyclic loads in which the irreversible material degradation is represented as a loss of stiffness in cohesive zone during the unloading portion of the load cycle. Similarly, people extended the capability of their cohesive constitutive model to account for fatigue damage accumulation during unloading. In all of these references, the fatigue damage accumulation is accounted for in a cycle-by-cycle analysis for high cycle fatigue where the number of cycles is larger than 106. A cycle-by-cycle analysis would be computationally interchangeable and interactable. Thank you so much for watching my video until the end. And here you can see that I have a geometry and the material, the geometry is for this one that will be mirror, and you can see the solid mechanics and fatigue as a physical module, and the stress, and also the life cycle response and the fatigue cycle factors, and stress cycle distribution and fatigue usage distribution. Also, you can download this simulation from my github.com/masterscript.